thunderstorm, we could, what is it? It's like a nuclear power plant. Anyway, but the sun is what gives us this energy. And so that's why we're going to spend a little bit of time talking about how the Earth uses the sun, how we need this energy in order to function. All right, so first things first. We call this, anything that comes from the sun is solar. All right? And that's an important thing to remember. You know, you have solar panels, you have, you know, anything that's solar powered is powered by the sun. This, I think, is a Latin name, sol. I don't know. That's a but it is a part of one of the words that I'm concerned about today. Just remember that for now. If there's some radiation that comes from the sun, it's called solar radiation, and that's what we see as sunlight, and actually invisible light also comes from the sun, which we're not interested in today. But I am interested in invisible light. All right. So the atmosphere, our atmosphere, catches heat from the sun. Some of the energy is actually reflected back into space because that's the way the atmosphere works. It's kind of a one-way blast a little bit. And it lets some in, some is bounced out. If you look on page 210, you see that picture. It shows that the sunlight hitting the Earth, about 30% of the sunlight that hits the Earth is reflected back off into space. 20% is absorbed by the atmosphere, and only 50% of it actually gets to the Earth's surface and is absorbed there. Radiation. Let's back up. If you want to transmit electricity from this point over here, we have an electric pole with insulators to another electric pole over here in a house. If you want to transmit electricity from over here to over there, we have to use wires, correct? That's the way that we get energy from one point to another. The cool thing about the radiation from the sun is it doesn't have to travel through anything. We don't have to build wires or air or anything from the sun to us. As a result, the sun can just sit over here 93 million miles away and just blast us with this radiation. The radiation doesn't need anything to travel through. It just gets here and the Earth absorbs it and uses it. One other interesting fact is if there was air clear from us to the sun, all our eardrums would be deafened. Like we would be completely stone deaf because of the explosions that the sun is making 93 million miles away would be too loud for us to handle. So it's a good idea for God to just take that air and make sure it's over here by us and not over there by the sun. And not the whole way between us.
Like what kind of explosion?
That's all the sun is. It's a massive explosion all the time. Think atom bombs times
So
millions.
so whenever the sun all of a sudden gets really strong and hot, that was just an explosion?
Well, there are solar flares that go off because, yes, basically massive explosions. It is kind of cool.
That is
It makes Hiroshima look like small potatoes.
Makes what?
Hiroshima, when the U.S. dropped the atom bomb on Hiroshima.
Hiroshima?
I thought it was here.
I thought it was Hiroshima.
I have heard it said both ways. I like Hiroshima better.
Why did they do that?
That was Hiroshima. Yeah.
Nagasaki and Hiroshima. Anyway, there is a term for how well something absorbs heat and light. We don't have sunlight today, but, or at least not to play with. That's because the clouds are in the way, and clouds, there's basically a unit of measurement to decide how well something absorbs sunlight. Clouds reflect a lot of sunlight, and that's why when we have clouds, it's reflecting a lot of light back toward the sun, back out into outer space. We wind up not getting as much heat when there are clouds. And that's one of the ways God regulates things, and that's why one of the reasons global warming is kind of can't work. But we'll get back to that here in a minute. No, maybe not today. So, clouds have a very low, we call it an albedo, or an albedo, I think actually. They have a very low albedo, which means they reflect a lot. So a white sheet of paper is a very low albedo. But the asphalt out here is black. It absorbs a lot of that sunlight and holds that heat. And it has a very high albedo. There's a chart on page 208 that shows you kind of roughly high and low albedos. If something absorbs everything, if you have a really dark black surface and it absorbs everything, it has an albedo of 1. That's as high as it gets. If something has an albedo of 0, that is as low as it goes. So if you would happen to have, well, I guess a mirror would technically have an albedo of approximately 0. The desert, sand in the desert has an albedo from between 0.2 to 0.4. It absorbs between 20 and 40% of the light. The ocean absorbs less, from 0.03 to 0.1. Clouds would have a really high albedo, or a really low albedo would send a lot of stuff back. Forests reflect quite a bit. Deserts would just absorb most sunlight, and that's what makes them hot. All right. Basically, radiation is something we call electromagnetic waves. Those electromagnetic waves are the same things that are in microwave to a certain extent. Although we don't get the bad ones because of our ozone layer stopping. But there's a question on the worksheet here. All right. Whenever we have incoming solar radiation, we have shortened it down. Incoming solar radiation. Some scientists thought they were smart, and they just took parts from all 3 of these words and made it one word. Kind of like radar, for example, is an example of scientists doing that in another situation. This one they do in, sol, and ation. It's not insulation with a U. That's when you put insulation in your house. It's a completely different thing. Insolation is, they use this word to tell how much radiation we are getting and how much warmth we get. We measure it in watts, same as we do electricity. And there are 3 factors that determine how much insulation we receive. The 3 factors are cloudy weather. Cloudy weather will reduce our insulation. Length of the day. And the third one is the angle of the sun's rays. You've all done the experiment, I'm sure. If you haven't, who teaches this sort of that you know, where you take a ball and a flashlight, you shine the flashlight on the ball when the sun's rays hit it at an angle, the energy is more spread out, and you don't get as much energy per square foot. But when the sun's rays are very direct, all the rays are shining on one small spot. It's very concentrated and you get very hot under there. So that's the third. It's the third thing that affects insulation. Make sure to do the whole part of question number 3. the second part, we're supposed to, I want you to circle the second half. Find the last one, maybe. There you go.
You don't want the exosphere probably.
Mr. Cal, which ones are we not supposed to do?
And they're supposed to do all of this. This is make sure you
There's
finish
not
number
enough
three.
lines for the exosphere,
Oh, my bad.
so I just left it out.
Yeah, it'll work now.